Imagine you're throwing a party. Invitations are long since delivered to 20 guests with a place and time, but there's been a last-minute change of plans and only 15 minutes to give everyone new directions. Even with your cell phone, that's still a problematic state update to make if you want the entire group to learn about the new meeting point in time. This is Data Skeptic Consensus, in the 17th installment in our series about how multi-agent systems achieve collective decision-making. 20 party guests might not be so bad, but what about a global-scale network with potential bad actors? Today on the show, I speak with Ted Yin about the recent paper HotStuff, Byzantine Fault-Tolerant Consensus in the Lens of Blockchain.
Hey everyone, this is Ted. I'm from Cornell University. I'm finishing up my PhD right now in my 5th year. I also work part-time at Avalabs, which is another startup I co-founded with my advisor, Gunther.
Tell me a little bit about your PhD work. What are your specific areas of interest?
Yeah, so I think for the academic part, as a PhD, I mostly work on distributed systems, and that sounds like a very broad topic. So more specifically, within the distributed systems, I mostly focus on consensus. And within the consensus topic, there are also different kinds of consensus protocols. I mostly focus on so-called Byzantine fault-tolerant consensus protocols, or BFT protocols, which are nowadays very hot topics because people are interested in blockchain technology and blockchains need such kind of consensus in order to work.
We'll definitely spend some time talking about blockchain, but Byzantine fault tolerance is not as new as blockchain, so it's an older theory. Could you help some of the listeners with the basics? What is BFT?
Absolutely. So, yeah, indeed, I think there has been misconception. Many people think BFT is some kind of new stuff, especially in that community, when we talk about blockchains. But to me, when I started my PhD at Cornell, this BFT kind of consensus is the coolest consensus I heard of at the time. And before I actually dive into that world. So what is BFT? So Byzantine fault tolerance, it has a weird name. So what is Byzantine? It sounds like the name of the old empire, in probably medieval or some time period. And the reason that this kind of protocol got its name is thanks to Leslie Lamport. So you may have heard of this researcher. He's very well known in systems community, including his works on Paxos, all sorts of consensus stuff. He also proposed the name for this new category of consensus protocols called a BFT consensus. And Byzantine just is part of the story if you read his paper about the whole consensus. So let's forget about the name of Byzantine. So what this protocol is usually about is maybe you are familiar with the non-Byzantine kind of consensus, or, people usually call them crash fault-tolerant protocols such as Paxos or RAFs. So those protocols, they work great and they're widely adopted by the current industry. Google uses Paxos as its core for cloud service. And the reason that we needed yet another category of consensus protocols is because this kind of protocol does not assume malicious behavior by the participating machines or nodes. So that means the nodes can only crash. The nodes can only, like human beings, they can only say, oh, I died. And then you just shut down or crashed without creating any noise into the channel or into the network. So then people began to think about how we should handle the case where there's some node that could go crazy. Say I'm a node, then when I die, I don't die peacefully, but I create a bunch of noises, and the noise could be interfering the entire network. And even worse, I could be, some zombie node controlled by the external attackers. So I could exhibit arbitrary behavior. Basically, I'm like the insider sent by some other party. So I'm like a spy in the system. So how do you handle this kind of situation in a protocol? While at the same time, you still want to achieve the same goal as the non-Byzantine one. Usually we call them, benign or crash fault tolerant protocols. We want to achieve the same goal, but with different assumptions.
Makes sense. And are there general classes within that domain of Byzantine fault-tolerant problems? Are there different schools of thought or considerations or shortcomings? I guess what's the lay of the landscape before HotStuff was introduced?
Yeah, that's a good question. So there have been very extensive studies over the decades, probably for almost 30 years or at least 20 years, revolving this topic. And for that, people thought about different models and mostly, assumptions that could be made to the network and also to the strengths of the adversary or the problematic nodes or machines in the systems. So most noticeably, if you view this landscape by looking at the network assumption or model, there could be three main categories. So the first one is, what about we do such protocol without compromising any assumption in network? So we still assume like in the network, the nodes can send messages to each other and the messages are delivered in the end within finite amount of time. Just we don't know how long that time is going to be. So that's usually called synchronous protocols. And one noticeable pioneering work is called Ben-Or. So it's a very theoretical protocol and it works theoretically. So it opened up a new path so people can do such no compromise protocol in theory. So we do not make additional assumption for the network. And that's the first category. But that kind of protocol does have its disadvantages. Mostly it's about whether it's practical enough. So usually in this category, protocols terminate within some probabilistic amount of time. So you can think of this process as throwing like a dice or coin. So eventually, that you cannot get all heads up when you throw a coin, but that's still probabilistic. So you can calculate the expected number of rounds until you reach an agreement or consensus, because our goal is to reach a consensus. But people then wondered, could we do better? Could we have more realistic protocols? And then there's another category, probably roughly at the same period of time, that is totally the opposite side of the aforementioned category. So for the second category of protocols, people wonder that if we can improve the protocols by assuming extra time delay assumptions for the messages. So for this kind, people will assume there's a little delta latency bound. In English, it's like we don't send messages to each other and assume they reply, within some unknown amount of time. We usually assume when I text you, you will reply in the next few seconds or just within a day. You would never reply to my message like 1 year later. That makes no sense, right? So that's something also could be found in today's applications. Programmers usually use timeouts or some, predefined assumptions about how long for a message to deliver to the other side. And so if you make this kind of assumption, you can know in advance in the network how long the slowest message delivery could take. So you can use that time bound to ensure that after a certain amount of time, for sure if you still cannot hear from the other side, then the other side didn't send you any message. So this category is usually called the synchronous type. So by the word, it suggests it's synchronous. So we are synchronized because we know that no message could take more than capital delta amount of time to be delivered. So that's a totally different model. And for this type of protocols, usually can tolerate more faulty nodes, Byzantine nodes who exhibit malicious behavior in the system. For example, first category, the asynchronous one, usually can tolerate up to 1/3 of the failures or the Byzantine nodes in the system, whereas the second category can take up to half of the failures in the protocol. So that's more tolerant, but it's at the cost of placing an additional assumption that no message in your network can take longer than some constant pre-known time to be delivered. So that's the second category. Then people started to ask themselves, whether we can try to combine these two together, because, these two are mostly like two extremes. The synchronous one makes very strong timing assumption, whereas the asynchronous one, yes, it's always safe and does not assume much about the network, whether we can combine them together or to find the best spot or the middle land between the two. And then here comes the third model. Usually it's called partially synchronous. So it's partially synchronous, meaning it has some synchronization in the protocol, but the reason that it's partial is because unlike synchronous ones, the synchronous ones will break if your messages take more than delta time to deliver. And that's a huge bummer to the system because you would never want the system to break in terms of safety or security. You may accept a system that runs slowly at times, but in general, you don't want it to break to compromise its consistency. So this last category that I just talked about is a good middle land between the two because on the one hand, you do have this non-compromised safety guarantee as the asynchronous protocols do. So, which means if your network becomes pretty unpredictable, meaning that some messages could take quoted forever, but actually within finite time, just you don't know when to deliver, you're still safe. So you're not making strong assumptions by assuming some messages or like all messages will be delivered within like say 1 second or 1 month, but you don't care. Like even if there were messages delivered like 1 year later, you wouldn't change your safety guarantee in the very end. So you don't actually break in this case. But on the other hand, there's a famous result called FLP impossibility. That's a very famous result. So what that impossibility says is you cannot have a protocol that is both safe and live, meaning it keeps running so it never gets stuck, and also satisfy consensus. It achieves consensus, both safe and live, and it does not place any additional network assumption, so there's no such protocol. And that's why you still want to make some compromise by saying, yes, I'm always safe, but because of the impossibility, I cannot get around it. And the way that I can still achieve a protocol is to assume that on a bad day, quoted bad day usually means that latency fluctuates, you have unstable delivery of messages, you have sluggish nodes in your system, and on that bad day, your safety is still intact, but your aliveness is not well guarded in that case. So that means if your system goes wild in terms of latency, then your protocol gets stuck forever. But usually by making the extra assumption that eventually the system could calm down and the messages will be delivered in time, within finite time, and also within some delta bound. We don't have to actually know the delta bound in advance, but the system will resume its processing. So that's more realistic. It sounds kind of wordy and complicated, but in short, it's just like it's a well-thought trade-off between the previous two types of protocols. And the previous two types were mostly theoretical, and this type is more practical as it always guarantees safety, and also it allows liveness failure, which is not a huge deal in many researchers' minds because you can wait for a system to process more information, but it's unacceptable if you have a security breach or safety breach.
I know a lot of the historical work, at least in, papers and textbook stuff I would read, started with, maybe 5 or 7 nodes, very small networks, which I guess at the time I was reading them seemed quite practical. I was working on LANs and things like that. It made sense. But of course, we live in the more internet age now where N can get orders of magnitude larger than that. Were there any limits in the historical work that became apparent as we tried to scale up some of these approaches?
If you take a look at the current realistic deployment of, say, not even BFT protocols, but benign ones like Paxos, usually people won't use more than, I think for Paxos, it's like 5 nodes. So it tolerates 2 crashing nodes, and that's enough. And I actually asked like a student here at Cornell, he once interned at Google, he learned about that. So according to what he's told me, Google usually just use, 5 nodes in a consensus group because as a rule of thumb, it's weird to have 3 nodes because it's still likely to have another failure on top of one failure. But it's very unlikely to have 3 nodes simultaneously failing, at least in their local data center. So that's why the rationale behind Google's choice of the group size. And on the other hand, the reason that they refrain from having more nodes, you will see a huge performance drop if you keep increasing nodes. It's not like linear kind of drop. So people would think, oh, the whole process is if you add more nodes, of course, since all nodes want to exhibit the same behavior, so you are duplicating or replicating the states of one single imaginary machine. So then you will see some performance overhead as you introduce more nodes. But usually people would assume, okay, such overhead or such tendency of performance degradation is linear. But if you think a little bit more about it, you would realize it's not linear at all. It's something like the trend is mostly like 1/n kind of thing. So you see huge drop as you initially increase the size of the network, and then it tanks at the bottom and rarely drops any further. So you will see some curve like that. And also, I think that curve shows up in our paper. And that's one thing. So there's a so-called leader bottleneck in these protocols because partially synchronous protocols employs a leader. And the reason that leader is more efficient, I think it's because instead of letting everyone propose in the system and then try to reconcile to one single choice of proposal, it's easier to have one leader proposing all the time, assuming the leader is non-faulty, like it does not crash or it's not malicious. So it's faster in that case. But, that also means that leader nodes suffers from a performance hit. And sooner it becomes like the bottleneck of communication across the network. So that's one thing I think is fundamentally shared by all these protocols that are based on votes and voting. But there's another additional overhead introduced by solving BFT problem. So what I just talked about, is generally applicable to benign and Byzantine fault tolerant protocols. But unfortunately, when the first practical BFT protocol came out, named PBFT, it's called Practical Byzantine Fault Tolerant Protocol. When PBFT came out, its complexity was significantly higher than the benign counterpart like Paxos. So Paxos takes linear number of message exchange or authenticator exchange if you talk about it in the realm of BFT world. So that means you send linear amount of messages, usually like if you're familiar with the big O notation, it's like ON. So it's perfect. I think it's proven to be like lower bound. It's great. But for PBFT, I think for its normal operation, it already takes like quadratic complexity, and even worse when you have something called view change, meaning that the current leader is regarded as faulty or problematic by the network, then you want to switch to a different leader. And during that period, you may exchange some number of messages up to like, depending on how you calculate it, but it's definitely more than quadratic. So that's the pain in this world, because we would like to solve the same problem, but we do not want to pay the extra price in order to let them be practical, realistic.
Thanks to this week's sponsor, Springboard School of Data. Did you know data science is a fast-growing career field with 650% growth in jobs since 2012 and a median salary of $125K? Springboard has identified that data careers are going to shape the future and has responded to that need by creating the Springboard School of Data, a comprehensive end-to-end data career program that encompasses data science, data analytics, data engineering, and machine learning. Each Springboard course is 100% online and remote, and each course curriculum is tailored to fit the schedule of working professionals. Every Springboard student graduates with a portfolio of projects to showcase their skills to potential employees. All of Springboard's data courses are supported by a vast network of industry expert mentors. Springboard's tuition-back guarantee allows students to secure the role of their dreams and invest in themselves without risk. Want to learn more? Springboard is exclusively offering up to 20 scholarships of $500 to listeners of Data Skeptic. Simply go to springboard.com/dataskeptic for more information. Yeah, I'd love to zoom in on the view change specifically. So as you'd mentioned earlier, that those rounds that the system is going through where it's trying to come to consensus, the leaders being established and sharing messages, that as N goes up, that's a very unforgiving delay then of how many messages have to be sent out to achieve consensus, at least in the historical models. I know this is one of the areas in which you and your co-authors and the contribution of HotStuff accelerated that process. What was making it go slow, and what's the core improvement there?
For this part, yeah, this is one of our major contributions that we would like to express in our paper. And I think for sure its complexity gets decreased. Then people started wondering, like, what's the secret sauce here? Or like, what makes it special? And how you manage to get rid of that annoying order of extra order of n. So to talk about that, we can actually zoom out a little bit, because before our work, there was a work called SBFT. So that work tried to also manage to reduce the complexity for normal operations. Because as I mentioned, for PBFT, it has the two modes or like phases or whatever. It's mostly like modes of operation. So for the normal mode, it operates just like what Paxos does. It's very similar. So you send out the votes, you propose, and all nodes send out their votes. And the reason that it's quadratic, the reason it has extra order of n, I mean, intuitively, you can think of it as the cost you have to pay for Byzantine tolerance. If you assume the leader never malicious, then you do not have to let the other followers to send out the votes to everyone else to cross-validate that. So in Paxos, you don't have to do that. You just leader sends out the votes, and then the followers respond, and the pattern is most like that. So in Paxos, there's no such, all-to-all broadcast, and we don't have to do that because we know the leader never lies. It could crash, but it never lies. But however, in BFT, you never know whether the leader is faulty. So then you always, as a follower, you're always skeptical about what leader says. So then you would like to fully exchange your information with each other to talk about the proposal. That's the root of the extra cost in normal operation. So one way to get rid of that, of course, is somebody call it cheating, but I'd say it's a good use of cryptography. So people realize that you can try to combine the votes into a larger vote, but not larger in the actual storage footprint. The magic here is there's something called threshold signature in the cryptography world. Something magical about this is there's a way to generate some binary data. You can call it a proof, but it's just like a null object, like a string. So that string represents or could be verified as a proof of like k out of n, assuming n is the total number of nodes in the network, then some threshold, some number of nodes out of the entire network have once voted for this proposal. So you can use only constant cost of binary data to represent the original linear amount of data. So then you get an order of n shrink in terms of complexity without ever changing the protocol paradigm. So that's how SBFT managed to cut down the normal operation from quadratic to linear. But what it couldn't do, though, is that the view change in such PBFT protocol is still fundamentally higher than linear because its complexity was at least cubic. Then even if you apply such crypto trick, it can only cut it down from cubic to quadratic. So how do you move from quadratic to linear? Then that means probably we should try at a different round. So in our work HotStuff, we tried a different approach. We got inspired by, I think, both the Tendermint protocol and Casper protocol. So I think there's a paper written by Vitalik, the leader of Ethereum, the crypto world. So he wrote like a draft on archive talking about how to use some voting-like protocol to finalize the decision on their blockchain. And we took a look at it. The description is unlike academic paper. It has relatively a vague description, but we got our inspiration part from it because we realized both Tendermint and Casper protocol revived some common technique or some lost technique in the past. So actually, I can expand a little bit more on this because it's very exciting. If you take a look at how PBFT looks like, you would realize that it's like the so-called DLS protocol, because that protocol didn't have a name. It was in a paper written by Dwork, Lynch, and Stockmeyer. So that's the first protocol that uses partially synchronous model. So of course, PBFT also uses the same model, and it got its inspiration from that paper. And I think it borrowed most of the concept, or inherited the spirits from the former work. But what it didn't use is there's some hidden or latent locking mechanism buried in the very old work, that DLS work. So in PBFT, it didn't do that. It instead chose a more Paxos-like kind of style. So basically, this is like, in an analogy, it's like you're trying to inherit some characteristics from your parents, but not all of them. You may lose some of the characteristics. And then we discovered that probably your ancestor has something that's very interesting that you didn't make use of. And then we derived our protocol entirely from scratch from that forgotten or lost part of a good part of the spirit. So what is locking mechanism? It's kind of subtle and it's hard to fully expand in such a short interview or podcast. I would sincerely recommend you to read the papers. But intuitively, I think it's mostly like, if you're familiar with chain style of stuff, like, blockchain kind of stuff, I think it's the blockchain world is complicated. I would not talk about its commercial part, all its craziness, or the fancy stuff in it. But I think if you take a look at how those blockchain protocols work, they use a very different paradigm. They don't do vote-based kind of approach, but they do have something that you try to vote on the prefix or on the path over a tree. So basically, you try to grow a tree of proposals. Then eventually your goal is to achieve consensus on the prefix or a path of the tree. And then it's very different from what Paxos or PBFT does, because for PBFT, it doesn't matter. The topology really doesn't matter because it just makes consensus on every slot of an imaginary array. So the ordering of, proposals is only enforced by some counter or numbers. But however, in those blockchain style of consensus, its ordering is imposed by topology. So that means you may have a different organizations of your proposals so that you can understand like the implication of the consensus better. And then you can make rules about the topology of the tree that you are trying to grow. That greatly simplifies the protocol design. Then that's how we managed to look at the same problem, but from a different view. So we didn't take the step, we didn't inherit from PBFT directly, but we took a step back and look at these protocols and their ancestor, and then found out that there's a way to cleverly dodge the bullet to avoid a complicated part of their, like say, view change design, but rather we use more chain-like kind of consensus. And then because we have better organization of things, we can have a clearer mind of where to actually cut down the extra costs induced by the view change. And overall, I think in short, if you have a takeaway message from what I dived into just now, is that because we don't distinguish the normal operation from the view change, so we unify them, then we can deal with the two problems at the same time and with lower cost. So we don't have to specially treat the extra process, which is the view change, and which took a larger complexity of messages compared to the normal mode. In our system, we don't have two modes that we switch around. We only have one mode. Like you just build up the tree, and as long as some patterns emerge on the tree, you get your finality. You finalize your proposals.
Yeah, that's a great summary. And I'll echo your comment that listeners should really look at the paper. I know we didn't get to dive deep into all of the different steps and the pre-commit and all these kinds of things, but the visual really helps in reading it there if you want to understand the deep nuances of the paper. But for me, as a high-level takeaway, you guys have very much best-in-class asymptotic results and also this responsiveness property. So your work in that regard is pretty fundamental. It's an improvement for state machine replication, which shows up in probably every industry. Does any nuance or quality of the work in your mind tend to some specific use case or application you think this will empower? Are there real-world cases we can attach this to?
Yeah, absolutely. I think this work is very interesting. I think to both, because Dalia, Mike, and I mostly devoted our time in this work, of course, and also Itai from the VMware. So we four devoted most of our time on this work. And I think I once had a conversation with Dalia. So we discussed about, the future possibilities of this protocol. And we both agree that it's uncommon. It's not about, praising ourselves. Oh, this is such a great idea, a smart idea, so we came up with it. It's so good. It's mostly like, could we really come up with another one, like with simplicity like this? And the answer is, we're not certain about it. So it's, coincidence. It's like sparks of our known knowledge. So it clash into each other. So then we finally came up with this protocol. And then we did envision there's a broad use of this protocol because it achieves exactly the same thing as PBFT does. So this is mostly like if you're familiar with putting up like a desktop computer, or if you're familiar with the processors, Intel versus AMD, which one I should go for, or you're familiar with gaming, like NVIDIA, AMD, which one should I go for? So now I think this is a good analogy. So in order to build a larger system, you need this kind of service. You need state machine replication. Either you do it for like proprietary system within like a corporate, or you want to do it for some fancy blockchain startup, permissioned use case. You want such a protocol. And in the past, the only choice, I think the only obvious choice for many people is PBFT and its variants. So there are also other asynchronous solutions, but in terms of performance, my idea is, PBFT is among the most practical one. So here we really tried hard to retire the old king. And I think in some degree we did, because according to our evaluation results, we see, with all this simplicity and also, of course, theoretical improvement in the protocol, we're still able to sustain the same performance or even achieve better performance because you have a simpler implementation. Then at the end of the day, we can say, any use case where PBFT is required could also be the use case, potentially be the use case for this protocol. And of course, one of which is some blockchain related application. So I remember in the fall of 2018, I think we spent some of our time selling our protocol, quoted selling, but not commercially, but academically, we tried to let others know, oh, here's a new protocol. It could be very cool, simple. You can implement it. It's good for the industry because it requires a lot of knowledge from the engineers to implement the protocol. Unlike PBFT, you have to understand all the math behind it. For our protocol, you just do what the constraints say, and it's very short and succinct. Then you get your protocol working, and it's always safe. In terms of performance, you can use your own heuristics to optimize it, but you never break the safety, as we already decoupled safety and liveness in our system. So you can just play with, different kinds of gadgets in your system without worrying about breaching the safety part, like the core part of the protocol. I think in 2018, in the fall of 2018, Facebook got his interest in our protocol. So I think we managed to convince Facebook into using our protocol, and they did spend a substantial amount of time to investigate the known, BFT state machine replication protocols available on the market, either in academic world or, white papers from other startups. And they finally settled down on this protocol. I think it's also a good backing point that our protocol could be useful and practical. So in their later project, Libra, although Libra, it's related to some political issues or some, legislation issues, it's still a good push to the crypto front. It's a large company for Facebook. Their protocol at its core is using this very same consensus. So that's nice use case of this protocol.
Very exciting. Well, Ted, thank you so much for coming on and sharing your work. This is a really interesting paper. I'm glad we had a chance to chat about it.
Thank you for inviting me to do this.
That concludes this installment of Data Skeptic Consensus. Our guest this week was Ted Yin. Claudia Armbruster is our associate producer. Vanessa Burciaga does guest coordination, both of whom have done a tremendous job recently with some last-minute updates on the production of the show. And lastly, I've been your host, Kyle Polich.